Okay, good morning again. Today's last talk is biases among classes of rank crank partitions modulo 11 by Professor Badri, Vishal, Pandey, University of Cologne.
Thank you very much for the introduction. I'd like to thank ICTS, the organizers, and all the audience for listening to my talk. My topic is a bit, slightly different from the general theme of the conference, but I hope that you enjoy the presentation. Okay, so today I'll be talking about my joint work with Professor Catherine Brinkman, biases among classes of rank partitions modulo 11. Okay, so here's an outline of the talk. So I'll start by defining partitions. Rank and crank statistic. I'll try to motivate why we want to study the biases among these things, and then I'll state my theorem. And to give an idea of the proof of the theorem, we need effective asymptotics for these rank and crank partitions. So I'll talk about that, and in the end, I'll give a short idea of the proof, how this works. Okay. So to start, a partition of a positive integer n is a non-decreasing sequence of integers that adds up to n. So we don't want repetition. So for example, 3 can be written as 2 plus 1 or 1 plus 2. We don't want to count them separately. So that's why I put an order. And P of n, the partition function, counts the number of such partitions. So for example, when n is equal to 5 can be written as either 5 or 4 plus 1 or 3 plus 2 or 3 plus 1 plus 1 and so on. So you can see that there are the number of such partitions are 7. So P of 5 is equal to 7. Okay. So I mean, partition function has been interest of study of many mathematicians, starting from Euler. There have been many great mathematicians who have worked on this. So one of the very significant names that comes up when you talk about partitions is Ramanujan. As a matter of fact, it's his work with Hardy on asymptotics of partitions that gave birth to the topic of the conference, the circle method. So that's nice. And as a matter of fact, Ramanujan actually gave so many, so many things that mathematicians still are, exploring those ideas. So one of them that is of like a particular interest to combinatorics people are these famous Ramanujan congruences. So he pointed out that he actually showed that partitions satisfy these congruence conditions in an arithmetic progression. So you look at the partition of a number of the form 5n plus 4, then it will be congruent to 0 mod 5. Similarly for primes 7 and 11. And these numbers actually are not random. So 4 is actually the inverse of 24 mod 5. Similarly, 5 is multiplicative inverse of 24 mod 7, and similarly 6. Okay. So indeed there is a pattern, and actually he proposed that these are the only such congruences. And it was proved later on using the theory of Galois representations. But the story of our talk, namely the rank and crank statistic, they actually, the origin is due to Dyson. So Dyson in 1944, he was studying these congruences, and whenever you have positive numbers in a sequence, people in combinatorics, they try to understand that, like they try to give a combinatorial interpretation of these things. So Dyson conjectured that there should be some idea that should be able to explain these congruences combinatorially. For that, first he defined the rank statistic. So I'll define it later, but let me point out that he started by defining rank statistic as a way to explain these three congruences, but he realized that you can only explain these first two congruences. And then he actually conjectured there should exist a third one called crank. So he defined what rank should be, but he could not define the crank. So rank explained the first two congruences, and he proposed that there should be another such a statistic that should actually explain the last one. And it took like next 40 years to actually come up with the definition of crank. It was due to Andrews and Garvan. So they, in 1988, they finally defined crank, and then the combinatorial interpretation was completed. Okay. So let me start by defining rank. So rank is pretty easy. So you start with a partition of n, then the rank of that particular partition is the largest part minus number of parts. So in this case, the largest part is lambda 1, so lambda 1 minus k. Okay, so here's an example. So a partition of 5, so when it's just 5, the number of parts is 1 and the largest part is 5. So 5 minus 1, 4. In the second case, you have the largest part is 4, the number of parts is 2. So 4 minus 2, 2, and so on. And you can see here that we allow it to be negative. Okay. How does this explain those congruences? So first we need to define, well, what we need to do is we need to divide these partitions according to the rank being congruent to some number mod c. So n of a comma c semicolon n is equal to number of partitions of n with rank being congruent to a mod c. Then notice, for example, here the partition of 4. So this fits into the arithmetic progression 5n plus 4 when n is equal to 0. And in this case, when you notice that there are a total of 5 partitions and each of them fall into exactly one of these classes. So for example, here 2 comma 2, so the largest part is 2 minus number of part is 2. So in this case rank is 0, so that's congruent to 0 mod 5 and so on. And in general, what it does is whenever you have a number of the form 5n plus 4, it exactly divides it in 5 equal classes, which means that indeed 5 divides because the summation over all of these is equal to the partition number. That tells us that indeed this is divisible by 5. And similar result is also true for the numbers of the form 7n plus 5. Okay, but they fail to explain congruences modulo 11. So here I have written the partitions of 6. So there are total 11 partitions. So indeed it is divisible by 11, but in this case you see here, like there are some where there is no partition, there are some where you have more than one partition. So it's not divided equally. So this sort of didn't explain this phenomena of these Ramanujan congruences. So to explain this, Andrews and Garvan define the definition of crank. Okay, so it's rather complicated. The definition is rather complicated. There's a more natural definition which comes from when you look it into a vector setting. So, but I'm going to I'll consider this particular form. It's rather easier to, I guess, put in words. So let the small o of lambda to be equal to number of ones in lambda, and let mu of lambda to be equal to the number of parts greater than number of ones. So note that it's not equal to the number of parts greater than 1, but rather number of parts greater than number of ones. Then the crank of a partition is equal to the largest part whenever you have that there are no ones, and whenever there is a 1, it is equal to the mu of lambda minus small o of lambda. Okay, so here is an example. So 5 in this case, in the first case there is no 1, so it's just the largest part. So 5. So in the second case you have there is 1. How many parts are greater than 1? There is exactly one part which is greater than 1, namely 4. So 1 minus 1, 0. Similarly, for example, here you have 2 ones. So O of lambda is equal to 2. So how many parts are greater than 2? There is just 1, right? So 1 minus 2, so minus 1. Okay. In this case, again, what you do is you define f of a comma c semicolon n to be equal to number of partitions of n with crank being congruent to a mod c. So, well, this picture is made by me, so it doesn't look nice, but I guess it does the job, I guess. Okay, so here you can see that when you look at the partitions of 6 modulo, well, 6 and divide it in terms of these like congruence classes, modulo 11, they fall exactly 1 in each of these classes. And indeed, in general, it turns out to be the case. I should also point out that actually crank also explains the first 2 congruences. So it's not only like explaining the third congruence, but rather all 3. But there is this difference that the way crank classifies these congruence classes is different than how the rank classifies. So it sort of gave this idea to mathematicians that what would like, can we compare these like, so we have studied these like in very specific arithmetic progressions, right? So what happens in these other cases? And that's sort of like motivates our work, the biases among. So we look at different arithmetic progressions and look at different congruence classes and see which of them is like bigger than the other one. Okay. Well, the study of such things was started by Lewis in 1997. He showed that, well, the parity of the partitions, that like so the bias among the parity of the partitions, like so this side is like number of partitions with the number of partitions of any integer 2n, which is even, and here it is like odd. So there is a bias among odd whenever your number is even, and there's a bias among towards even ranks whenever you have an odd partition. Sorry, odd numbers partitions. Okay, and actually later on Andrews and Lewis showed that actually this inequality switches when you consider, instead of rank, you consider the crank. And in the same paper, they gave the following conjecture. So these first 3 are regarding the rank and the last 2 are regarding the crank. Sorry, the first 3 are regarding the crank and these are regarding the ranks. The first 3 congruences were actually proved by, the inequalities were proved by Kane. The last 2 inequalities were proved by Brinkman. Okay. So, and then after that, there have been many such studies, like for different, you instead of like 2 or 3, you choose different numbers, and you look at like different classes and see how things work. So our work was motivated by a recent work by Borozenets. So what he did was he considered these rank partition statistic modulo 11, which is pretty natural because rank and crank, well, they are like their origin is to study these congruences modulo 5, 7, and 11. So 11 is one of those numbers. And actually using some combinatorial arguments, he proved many interesting like inequalities among them. And there were some that he could not prove, like his techniques didn't allow him to prove, so he put that as a conjecture. And in this paper, we prove these conjectures. So what are these, now there are theorems. What are they? So here is the notation. For 2 sequences A and B, we say A less than subscript capital N of B means that this inequality is satisfied after this capital N. And the shorthand, n capital N sub j comma d of n to be equal to, the partitions of the integer 11n plus d, which are congruent to, whose rank is congruent to j mod 11. Similarly for the crank, and p sub d of n is equal to partition number of 11n plus d. Okay, so then the theorem is the following. So we have all these inequalities. So for example, what this tells you is that when you look at the partition of the integers of the form 11n plus 0, so 11n divided by 11, then they are less than equal to the partitions of 11n with rank being congruent to 0 mod 11. Okay, and here's some more. So how do we prove these inequalities? So we are going to use analytic methods to prove these inequalities. So for that, first let me give you the generating functions for rank and crank. So the first one is the generating function. So here m, capital M of m comma n denotes the, it's the number of partitions of n with rank being exactly equal to m. So, and from here you can see that there is a symmetry when you like replace zeta by zeta inverse. So because of this, right? Similarly for the rank, you have the similar symmetry because of this again. There are two factors, one has zeta and the other one has zeta inverse. Here again, this is the Q-Pockhammer symbol given by this. Okay. All right, so, but we are not interested in exactly this, right? So we are interested in not like, so partitions with rank being exactly equal to m. We are interested in partitions like partitions with rank being congruent to say A mod some C, right? So how do we get that? Well, we are going to use this symmetry between zeta and zeta inverse, and also the orthogonality of roots of unity to write the following. So what you do is you multiply by some factor of, so you replace this zeta by some 11th root of unity and multiply by the right power of zeta and then take a sum over all the possible classes of, all the possible 11th roots of unity. And you get this. Now the interesting thing is that you see we can, so we get this one factor here and this thing here, and if you go here, so we are interested in like comparing these two things, right? Which essentially means that what we do is we send this the other side and we want to show that, well, for specific values of A, C and N, this difference is either positive or negative, right? So we are interested in, well, we can understand these things by understanding what these are, which essentially means that we want to understand these. Like these, this rank generating function, crank generating function evaluated at a specific root of unity. Okay. Any questions so far? Okay. All right. So, so we give this short like notation. So your rank. So yeah. So I'm going to work out everything. Well, sketch out everything in the case of rank, and similarly you can do it for crank. So what we look at. So we are interested in 11th root of unity, right? So we are interested in congruence classes modulo 11. So we look at our rank function and we replace our zeta by zeta's like 11th root of unity to the power j. So that's also primitive 11th root of unity. And we write it as summation n is equal, n greater than equal to 0 b sub j of n q to the n. Okay. And what we are interested in is like summation over all j, varying from j is equal to 1 to c minus 1 by 2. So in our case, c will be 11. So 11 minus 1 by 2, so 5. J is equal to 1 to 5. Okay. So then actually we have a nice asymptotic formula for this. We need these special functions. So this one is a Kloosterman type sum, and this is a Kloosterman sum where there's some root of unity. Well, in terms of these functions, we have the following theorem due to Ringman. So here she used circle method and on apple-arch sums to get these asymptotics. Here it's not effective. There's a big O term, and the meat of our or this like work was to actually determine like get an explicit bound on these ones. Okay, so to our results, we need an effective version of this theorem. And what is that effective version? Well, it's the following. So we have that b sub j of n for j lying between 1 and 5. That's the one we are interested in. Oh, by the way, I should point out that there's a general formula. So I have written this down only for c is equal to 11, but this is a general formula where this 11 can be replaced by any c. an integer c. Okay. Yeah. So b sub j of n is has this main term, and there is an error term which is bounded as follows. Okay. Now note that, well, this is non-zero whenever your j is well, so we have that j lies between 1 and 5, so the only possibility is when j is equal to 1, right? And that is the case when this is, so what I'm saying, so we are looking at this summation over b sub j, right? So the main term will come from j is equal to 1 case. Okay. And then from here you see that in the previous theorem, we can choose epsilon to be equal to, well, 5 by 4. Okay. So let me quickly go over the idea of the proof. So here what we do is, so the thing is like the main term comes from this one when k is equal to 1. Okay, that's the main term. So what we do is we bound the, we put this in error term and this in error term except for the case k is equal to 1. That's what we are doing here. So there's the first case. You can well, here we actually use all the trivial bounds that we have. So this is in absolute value, this is less than or equal to this summation. And here this is actually less than or equal to 1 over this sine pi over 11 times summation, so basically k. So that's why you get this, this square root of k in the numerator, and then you can easily evaluate this. And you get something like this. Okay. Similarly, in the second term, so here you see that k is not equal to 1, so k starts at 2. So that can be, in a similar way, pretty much bounded by this. So here we have the same factor as in the main term, but this factor is different. So instead of there you have 5 pi by 5 pi times this thing by 66. Here it's 132. Okay. So and the most complicated terms were big O terms because they actually involved. So when you are applying the circle method, then there are many integrals that you get. That generally you put show that it's very small, so you put it in a, well, in a big O term. And what our work was to try to understand that and sort of bound them. So I'll show you the easiest one that looks something like this, where this is actually coming from R. So first let me show, let me tell you that these things can be trivially bounded again, except for this factor, which was coming from a special value of your rank function. So here is where you can see that instead of z in the numerator, you have I over z. So h prime plus I over z. So this h prime is basically you are looking at a matrix. Well, you are looking at something like h comma. So a matrix which has h comma k in one of its one of its column, and then h prime is sort of multiplicative inverse of that h modulo k. Well, negative inverse, I guess. Okay. And actually the good thing is that now we can choose specific values of z, and we can approximate this using, well, we know how the generating function of this looks like. So we can put that in computer and we can approximate this to get the following. Okay. So using this, you can get the big O term to be less than or equal to this. The good thing is that it doesn't have this sin h term, so this will go to the error part. And similarly, there were 4 more integrals, simpler integrals, and from there you can actually get these bounds. Okay. And when you combine all these, you get the result in the end. And the biggest power of n comes from this factor. Okay. All right. So similar things you can do for crank. So I'll show you the result, and I'm not going to show you exactly how it looks because it's something similar. It was rather a bit complicated. There were some, so this part, evaluating this part was rather complicated because we didn't have the exact right form where the specific values of parameters here were giving us exactly this. So we had to reverse track everything and get, well, new values for the crank. So here again, we have similar sort of special functions. And in terms of these, due to one of Catherine's students, we have the following asymptotic. Again, this is not for 11. I have specialized in the case of 11. This is the general result for NEC. Okay, and the effective version of the theorem is the following, that a sub 0 comma 11 of n is, the main term is given by this. It doesn't have that delta factor anywhere. Oh, sorry, it is here, but it sort of doesn't matter much, right? So that actually it does matter. Sorry, it has, yeah. So there is a delta factor here, and the error term is bounded by something like this. In this case, epsilon can be chosen to be 3 by 8. Okay. So again, recall the theorem, and I'm going to actually, well, sketch out a special case of this. Okay. So that special case is this. So just keep this one in mind. So this, using this, will show actually these inequalities, these ones, like, so between M and P. So define C sub A, so 1 of n to be equal to this, this crank minus P of n divided by 11. And for example, this inequality simply means that we are choosing A is equal to 1 and n to be equal to 11n plus d, 11n plus 7, right? So we are looking at this when A is equal to 1 and n is equal to 11n plus 7, okay, and here 11n plus 7. And we are trying to show, so for example, this means that we want to show this thing is greater than equal to 0, sorry, greater than 0. Greater than equal to 0. Okay. Okay. So how do we do this? Well, it's, now we have all the tools. So this being greater than equal to 0, we can actually combine all of these together. So we define S1 to be this set and S2 to be this set. Then we have to show that this difference is either positive or negative depending upon A comma D belongs to this or this. And if you write it in terms of the A functions that we had, it is written by like this. And again, remember that the main contribution was coming when J was equal to 1. Okay, so that's the main contribution, and everything goes into the error term. Well, I've actually reversed the order. First, what we do is we sort of like look at this function, the estimates that we have, and actually we see after which point these actually start satisfying these inequalities. And putting it in computer, we can actually show that for n greater than equal to 0, these are positive whenever A comma D belongs to S1 and is less than 0 whenever A comma D belongs to S2. And then we check in computer that for n less than equal to 79, what are the exceptions? Okay. Well, there is a nice way to combine this into 1, and that's given by this. So you have this factor, this product, and you want to show that this is less than 1. Okay, where this function is given by this. So either you can put it in computer or you can work it out by hand, where you have to replace this m by like 11n plus d. And when you put it, I mean, you can work it out by hand, or you can put it in computer, and then it gives you the result. So, and similarly in all the other cases, we can try a similar method. So it's not too complicated once we have the asymptotics, the effective version of that. Okay. So that sort of finishes the sketch of the proof. So yeah, so that ends the talk.
Great, thank you very much for the nice talk. Are there any questions?
So if you define like a partition function, I mean, not for all n, let's say.
Sorry, can you?
Now fix some, let's say A.
Okay.
And look at all the integers more than or equal to A. Look at
all the integers?
Which is more than or equal to A. It is small a.
Uh-huh.
Now define partition of n. Now look at the partitions are at least, I mean, each individual part at least A.
Mm-hmm.
Now define such a new partition. Now define similarly like rank and crank.
Mm-hmm.
So how will that means what is the behavior of that? I mean,
yeah, I haven't looked into it. I mean, it might be something that that I guess I think I mean I guess once you have the generating function, you can like check it in computer, right? So I haven't looked into it, so maybe I don't know.
Can we expect biases modulo other primes like modulo 11?
Yes, yes. So indeed, I mean, there should be biases. The most interesting cases will be where, well, these equalities hold, right? Yeah. So generally, you expect there should be some biases. The point will be when there are equalities.
So is it true that modulo every prime there will be some bias?
Yes, yes. I think there is a general result, not effective version of it. So there are results which say that if it's if n is big enough, then you have these biases. So if you look at arithmetic progression, then if n is big enough, then they have these biases. Like it's not interchanging. So it after some point it becomes like one is bigger than other.
Okay. Thank you.
Okay, are there any more questions?
Yes.
Yes.
So what are the properties these generating functions can have?
Like these functions?
Yeah, generating functions for your.
Yeah, so okay. So the rank function, both of them have some modular properties. So the crank function is very nice. It's a Jacobi form of
Oh, yes.
of weight half and index minus half, I think. And the rank function, even though its definition is actually nice, it is rather complicated. It's a mock object, it's a mock modular form. So it can be completed into a harmonic mass form. And you can use you get all these actually asymptotics using these modular properties of that.
So Jacobi form for level are just
For SL2Z, the whole full level.
full level.
Any other questions? If not, let us thank all the speakers first.